As he just said, I am a neuroscientist. Last year, I spoke to you about the effects of environment and experience on the brain. And this year, I'm going to tell you about the effects of programming on the brain and the effects of the brain on programming. So, brains, everyone has them, contrary to popular belief. They could technically or kind of be referred to as the wetware in our head, and the wetware that interacts with the software and hardware that we use in our everyday lives. Now, our brains are composed of various areas that perform different functions. So there's localized specialization within the brain. The frontal lobe is involved in cognitive processes such as personality, interpersonal connections, consequences of action. The parietal lobe is involved in representation of your body and the space around you. And this guy here is what we call the homunculus, the little man in the brain. That's how your brain sees your body. So the proportions on the homunculus are equivalent to the density of receptors within your body and the area of brain space dedicated to each part of your body. The occipital lobe is involved in processing vision. Your temporal lobe is involved in auditory processes and language processes. Your cerebellum does sensory motor coordination and balance, and your brainstem is involved in more basic functions such as maintaining breathing and reflexes. And the reason why we know what these areas of our brain do is because of case studies. So this guy is possibly the most famous man in neuroscientist. His name was Phineas Gage. He was a foreman working on the railway building projects in the West and had an unfortunate workplace accident where an iron rod was blasted through his skull. It took out one of his eyes and half of his frontal lobe. And this is how we know that the frontal lobe is involved in higher cognitive processes and things like interpersonal relationships and formation of personality, because following this accident, poor Phineas had a completely different personality when he came out of recovery. Horrifyingly, he was conscious during the entire ordeal. And while the surgeons were working on him, he described the sensation of parts of his brain slipping down the back of his throat because it was falling down into his throat. Yes. If you want to read more about it, actually, this book is really, really good, The Dueling Neurosurgeons. It describes his case study in great and horrifying detail. The other most famous man in neuroscience was patient HM. Now, he was a young man who had terrible epilepsy, and the sort of standard treatment for epilepsy in those days, around the 1950s, was to simply remove the part of the brain thought to be causing the seizures. So HM went in for surgery, and the surgeon basically stuck a straw in his head and sucked his hippocampus out. And this is how we know the hippocampus is involved in formation of memories, because after that surgery, HM was never again able to form declarative or functional memories. So he stayed forever at the age of about 25 on the day of his surgery. He could not remember that his parents had passed away. He could not remember where he lived at any time after that. He did not remember any of the hundreds of researchers that he met hundreds of times in the next 60 years, while he basically became a permanent case study. And again, his case study is covered really well in The Dueling Neurosurgeons, if you're interested. Nowadays, we have technology to look at what the brain does. So we don't have to rely on horrifying accidents or terrible surgeries to tell us what different parts of our brain are doing. And the technology that we use to do this is what's called functional magnetic resonance imaging. It's basically a bunch of big magnets that spin around your head and measure the movement of blood within the brain. So oxygenated blood and deoxygenated blood have different magnetic properties, and the idea behind fMRI is that when part of the brain is active, oxygenated blood moves to that part of the brain and deoxygenated blood moves away, and this differential in magnetic properties is picked up by these big magnets, and that's how we measure the brain's response to particular stimuli or tasks that we give to people while they're in this machine. And this was a study. This paper will be provided on the repository for conference materials. This was a study done in 2014 where this group actually looked at what programmers were doing while they were in an fMRI. So they were given little bits of code that were pre-tested for difficulty and time to solve. they undertook 2 tasks, comprehension of code and syntax of code, and the tasks were designed that there was minimal motor output in response to the tasks, so they had to either click a button in their right hand to say they understood what the code was doing, or click a button in their left hand to say they didn't understand, and that was done to minimize any other brain activity so that you could just pick up what coding was doing. And then the people who took part in the study then were sat down after they'd been in the fMRI machine and tested to see whether they actually understood the code, which was Java. I know this is a functional programming conference. I'm very sorry that they used Java. So these little snippets of code had to be really easily solvable, so in less than 2 minutes. There was no recursion, and they were designed to induce bottom-up rather than top-down comprehension, meaning that you can read it line by line and understand what the code's going to do without having to have domain knowledge of Java. So therefore, you're not going to be using your memory or other higher cognitive processes, because Java, that are unrelated to programming. So they're going to pick up just what comprehension is doing. Now, the syntax tasks were also identical to the comprehension code, except that there were 3 errors in each little batch of code. Again, the errors had to be able to be picked up quickly, and again, the tasks were designed to be pattern matched without having to actually understand what the code does or understand Java, so you're not activating other parts of the brain that aren't involved in just picking up these errors. So they collected brain activity during the comprehension and during the syntax tasks, and then they subtracted the syntax activity from the comprehension activity. So they basically took away bug finding brain activity from code understanding brain activity. And so this image here is what your brain looks like when you're understanding a piece of code. So the parts of the brain that are involved in coding comprehension are areas 6 and 40, which are involved in working memory and attention, and also a whole bunch of areas that are involved in language processing. So these are areas 44, 21, and 47 down here. So therefore, understanding code requires the ability to problem solve and also understand language. Going into it a bit more deeply, areas 6 and 40 are located in the frontal lobe and also the parietal lobe of the brain. Now, if you remember earlier, the frontal lobe does higher cognitive processes, and the parietal lobe does representation of your world around you. And these 2 areas in particular are involved in processing attention, in reading, working memory, and also in the more kind of nebulous area of problem solving. The language areas that were activated were 47, 44, and 21, and these are involved in what we would call the traditional language processing circuitry in the brain, which consists of Broca's area in the frontal lobe and Wernicke's area in the temporal lobe. And these 2 areas are joined by a tract of white fibers called the arcuate fasciculus. And now these 2 areas do different things. Area 21, which is located in Wernicke's, does speech comprehension and production of words, and areas 47 and 44, which are located in Broca's, does complex grammatical tasks. And you get funny language aphasias if one or the other areas are damaged in the brain. So if you get damage in Wernicke's, you are no longer able to produce the words that you want, but you can make perfectly grammatically correct sentences. If you get damage in Broca's, you can produce the correct words, but your grammar is completely scrambled. So again, people who've had strokes have showed these aphasias, and this is how we know what these parts of the brain do. So in summary, from that study, we see that many regions of the brain are involved in understanding programming and their associated skill sets. And these involve attention, reading, working memory, problem solving, and language processing, which then brings us to the question you all want the answer to: is there any way you can train yourself to become better at these tasks? So I'm going to run through them one by one, and I'll start with a definition. So attention is the filtering out and selection of objects from your visual field. So it's thought to undertake 2 processes. There's pre-attentive scanning, where you pick up really obvious differences. So looking at this figure here, with your pre-attentive scanning, can you find the really obvious differences? Yes. There's also focal attention, where you pick out really finely grained differences and focus on them. And this figure also has an example of focal attention in it. I'll give you a couple of seconds to see if anyone finds it. there's T's. And they are actually different to the other symbols. So this little figure shows you how attention works. You have your pre-attentive scanning, and then you also have focal attention, where you have to go through and sort of parcel up information a little bit at a time to find really finely grained differences. Attention can also be thought of as a spotlight. So you have competition within your visual field for what you're going to pay attention to, and your brain kind of has to filter out the things that aren't important and focus on the things that are important. And this is an example of a spotlight of attention. And I'm just going to run you through this video. Hopefully it works. No! Come on. Nope. Sorry about that. I thought that would work. It did not. Brief pause for technical difficulties. I tested this as well.
This is a test of selective attention.
Okay. So I'd just like you to follow the instructions. Okay, did anyone count the passes? How many passes were there? 15 was correct. Did the people counting the passes, did you notice something else? Yes. Who didn't see that? Who didn't see that? Yeah. So you were focusing your attention. You have good attentional focus. That's good that you didn't see that. But this is an example of how the spotlight of attention works. You didn't pick up the fact that a gorilla walked through the middle of that video. All right. So you see you have competition for your visual processing capacity. We know within the brain that there are both chemical and electrical signals. Chemical signals work at the level of cell-to-cell communication, and electrical signals work over circuit and system communication. And as a result, your brain actually produces a variety of electrical waves. These are called brainwaves. And your brainwaves can be indicative of a particular state of mind. And the brainwaves that are thought to be most important for paying attention to tasks are beta waves, which occur when you're in alert and working state. Now, these guys, this study here, did what's called neurofeedback. So they used an electroencephalogram, which picks up your brainwave activity, and they showed participants their brainwave activity on a screen and told them to focus on making one or the other types of brainwaves stronger than the others while they were undertaking what are called divided attention tasks. Now, the attention tasks that they were run through were a sound task where you have a high tone played in your left and a low tone played in your right ear, and you have to respond to one and not respond to the other. And also the Tovar Test, which has been described as the video game from hell, where you have a variety of visual stimuli that are very, very, very similar to each other, flashed up on the screen really rapidly, and you have to respond to one type of stimuli and not to the other. And it's used to test, let's see if that'll work. No! It's used to test impulsivity and ability to pay attention, and I'm just going to do this. So this is just a quick example of what the Tovar Test looks like. So this kid's undertaking the Tovar Test, and he's got particular images flashing up on the screen, and some he has to respond to and others he doesn't have to respond to. And that's probably enough of that. So these guys, while they were undertaking these tests, also were focusing on training particular brainwaves of activity. And this study did both beta and sensory motor rhythm waves. And the results that they found were that focusing on your EEG activity actually improves your ability to pay attention. So they undertook 2 of these tests, one without and one with the neurofeedback. And then these results here with the sensory motor and the beta wave feedback, this is the error difference between the first and the second tasks. So first amount of errors minus the second amount of errors. So if it's close to 0, it's about the same. If it's positive, it means there were fewer errors in the second lot of testing. And then omission changes as well, where you might miss some of the stimuli, were less in the subjects who had sensory motor feedback. And beta wave feedback improved reaction time in the Tovar test. So being aware of what your brain is doing during a task allows you to actually improve performance in that task and pay more attention in that task. So this is a way that we can train our attention. Moving on to the next function that was involved in programming is working memory. So working memory is an active process where you're actively trying to remember something. It's about 7 spaces or 7 digits long. It is not short-term memory. I do not like that term. There is not technically a short-term memory. So it's temporary storage of what's happening currently in an attempt to kind of integrate your previous knowledge with current situations and plot appropriate responses to your environment and what's going on around you. And again, you can train your working memory using neurofeedback. I'm not going to bother with that video because that was just an example video. Again, there was a study where they looked at EEG activity during these sort of memory tasks and told people to try to enhance a particular signal. And in this case, that was the sensory motor signal. And what they did was ran them through a conceptual span task. So conceptual span task consists of being flashed really quickly, stimulus words while you're in the fMRI, and then having to remember them afterwards. And you get 4 stimulus words that are associated with each other and 3 groups of these words, and then you have to do that 4 or 5 times in a session, and I'm going to take you through what that would look like. So this is just one session of what a conceptual span task would look like. And you're in a machine with the magnets whirring around your head, and you then have to name all the countries. Can anyone do that? And then name all the animals. Yep. And then name all the body parts. So this is what we get subjects to do during neurological studies. And then that is just one session of the conceptual span task. So someone undertaking this study probably got about 4 or 5 of those blocks thrown at them all at once while they were lying in the fMRI machine. And they did 2 sessions of testing, and in between were told to concentrate on their sensory motor brainwaves. And what this study found was that concentrating on your sensory motor brainwaves increased the amount of correct memory retention, increased the recall, and also decreased the number of errors during this memory task. So again, we see that knowing what your brain is doing allows you to actually improve performance on a task. Now, not all of us have access to this high-level equipment, unfortunately. There are other more simple methods for improving your working memory. The Dominic system and the major system are the favorite methods used in memory Olympiads. If you want to get really nerdy and really into memory, it's actually a competitive sport. So the Dominic system and the major system use associative features to remember things. So for example, if you want to remember the numbers 8 and 1, you think of a fat snowman holding a broomstick, and the fat snowman is the 8 and the broomstick is the 1, and you sort of walk through a landscape in your head looking at all of these various stimuli, and that's how you recall particular combinations of things. People in memory Olympiads can memorize the order of up to, I think, 4 or 5 decks of cards in about half an hour, and then they can sit there and just spout it back. It's fairly impressive. There's also memory palaces, which are a really old system that people use to improve their memory. And that's where you walk through a house or a palace that you've created in your imagination, and you have stimuli there to sort of jog your memory. So, for example, you might remember that your mum hates cats, but she likes going skiing and sitting in a garden, and she has blue eyes. And that's how a memory palace would work. Of course, if you're actually using these techniques, the more unusual and grotesque you can make the stimuli, the better you will remember it. I wasn't going to do that as an example. So we've seen how we can improve our attention and our memory, but how can we improve our problem solving? And this one's a bit more difficult to tackle because problem solving involves various areas of the brain, and it's kind of this nebulous cognitive concept. So we know that during problem solving, the ideal sort of brain state to be in is what we call flow, which you guys probably also refer to as in the zone or code mode. It gets called code mode in our house. And that's where you're fully focused and absorbed in, and you're enjoying what you're doing, but you're also finding problem solving really easy. And again, we know that particular brain waves are associated with particular states of mind, and theta waves are thought to be the most important for flow state. And there's been a bunch of studies showing that theta wave increase is related to improvement in attention, how much workload your brain can handle, how much memory your brain can handle, and also working memory performance. And even though I did just mention that EEGs are difficult to access, they are actually getting cheaper. This company here, if you wanted to set up your own system at home, actually sell fairly good equipment. They advertise at the neuroscience societies that I go to. And I am going to show you this video because it's really cool. If this will cooperate. So this is competitive drone racing using EEG signals to control, oh, go away State Farm, to control, to control the activity of robots in real time. So this guy has a little mobile EEG system hooked up to his head, and he's controlling the activity of that drone copter just by thinking at it, which is kind of cool. So you can do this at home with your own systems, and if you are interested in getting more into it, this organization here actually runs conferences and training seminars and stuff on both programming the software to go with EEG and also displaying kind of the cool stuff that people are doing. Again, for a more low-tech approach, you can train yourself to enter flow state more easily by learning how to problem solve more efficiently. And we know from various studies into how people learn that just kind of leaving, as Chris said last night, just leaving someone on their own to figure out a problem by going to Stack Overflow and searching for things is not really the optimal way to learn how to program. So we know that guided questioning actually makes people better at problem solving. How you might address this in the programming community, I'm not sure. I know that there's not a lot of sort of formal pedagogy outside of universities, unfortunately. And again, as well, being explicitly trained in how to solve problems helps you approach problem solving better in your everyday life. And then the very boring thing of just lots of practice. So one example of flow state and flow state that's entered really easily is when you get in your car and you drive from home to work and you realize you don't remember how you got there. And you get out of the car and you go, oh my God, I don't remember driving. That must have been really dangerous. It's actually really safe because your brain has entered flow state because you're doing a thing that you've done so often that you just kind of, your brain takes over and just does it automatically, and your reflexes are actually better when you're in that state than when you're consciously trying to do it. So far we've seen that many regions of the brain and their associated skill sets are used during programming, and that we can work on improving the skills involved in programming, either using high-tech approaches such as EEG and fMRI neurofeedback, or low-tech approaches such as training in better problem solving and memory work. Now, the biggest chunk of brain activity that was dedicated to coding comprehension was actually from language processing areas. So we have a really big part of our wetware dedicated to language processing. It's kind of a big deal. It's how we communicate with each other. And again, we have that classical language loop of Broca's, which is involved in production, and Wernicke's involved in comprehension of language. But there are also other parts of the brain involved in language production and assessment. And these include the conceptual system, which is a dormant system that provides the features or details of things. So your conceptual system knows in different parts of your brain that basketballs are orange, basketballs are round, and they bounce. Your mediational system joins all of those concepts together, so it kind of gathers in all of that information, and your implementation system gives you the language required to produce a sentence along the lines of, "I am bouncing around orange basketball." So how can we improve our language ability? Well, given that parts of the brain involved in processing natural languages are involved in processing programming languages, we can look at how natural languages are processed in the brain to maybe improve how we approach programming or how we teach programming or even learn programming. So we know that monolingual versus multilingual individuals have different levels of brain activity during language production. So this study here shows you a multilingual versus a monolingual individual. Multilingual individuals dedicate more brain area to language than do monolingual individuals, and it's also less lateralized, so they get activity across both sides of the brain rather than most of it just being on the left-hand side. I would be extremely curious to see what the brains of coders who know more than one functional programming or more than one programming language would look like, whether they would see similar differences. We know that these differences in the brain show up in people who have learnt second or more languages early in life. So unfortunately, if you're past the age of about 12, it becomes more difficult to pick up languages, and you don't get this increase in brain space dedicated to language processing. Most people don't learn to program before the age of 12, but the good news is that you can learn new semantic information throughout life. So you can learn a new language while you are older. It's just a bit more difficult and you won't have as much brain space dedicated to it. Whether this means we should approach learning to program the same way you would approach learning a new language is a question maybe for people who know more about how to teach or learn programming. Where you might have something like flashcards to learn vocabulary for particular programming languages, or immersion to learn a particular programming language, which has been shown to be the most effective way to learn natural languages. How you would do immersion, I don't know. I don't think you can speak in Haskell, but it's a potential, maybe new approach for how to learn programming. All right, so we see that many regions of the brain and their associated skill sets are used in programming, and that you can work on improving these skills, and that learning to program is like learning a new language and then having to solve problems in that language. So it's not actually an easy task. It places quite a large cognitive load on your brain. So knowing that, could we better design programming languages to take advantage of our brain's natural proclivities? So we have all this wetware dedicated to language processing. We also have a whole heap of wetware dedicated to face processing. Faces are really important to the human brain, to the extent that we get this phenomenon known as Pareidolia, where you see faces in things that aren't actually faces. So you see faces in the clouds, you see them in fruit, you see them in food, you see Jesus on your toast, these kinds of things. And there was this mathematician way back in the 70s who went, well, humans are really good at processing faces. Why don't we use them to represent mathematical things? So Chernov invented what are called Chernov Faces. They're a little bit creepy, but they're also kind of cool, where each facial expression represents a different point in k-dimensional space. And so this was a system that was much easier to read, apparently, than sitting down and going through a whole heap of numbers. Whether you could convert something like this into a programming language, I don't know. That would be an interesting challenge for whoever might take it on. So now that we've learnt a bit about how the brain processes programming, I'm going to do a little bit of a rant at the end about how programming is actually helping the brain and also helping in biomedical research, because that is my field. So we know that there are lots and lots of biological and medical challenges that honestly biomedical research is just kind of not going to solve. Things like paraplegia, quadriplegia, stem cell treatment is promising, but I honestly think that tech will get there first. And one example of this is the wireless transmitter technology that's currently being tested by a group in Melbourne in Australia, where they have developed a really, really tiny transmitter that you insert via the jugular vein, and it goes up into the motor cortex part of the brain, and then it transmits signals from the motor cortex to eventually, they hope, either a wheelchair or robotic exoskeleton, allowing people who've been paralyzed to regain a greater range of function. They're currently testing it in sheep. I know that they're scheduling clinical trials for next year, and that's actually a really cool and really promising technology. And most of you have probably read the Wait But Why post on Elon Musk's, you're all sitting there going, yes. This is similar to what Elon Musk wants to develop. I haven't read that post yet, but I am open to having discussions about it because I have opinions. I probably should read it at some point. Another example of using programming really effectively in medical treatment is for voice analytics software. So this is a group at the University of Michigan who have developed an app that goes on the phone of patients with bipolar disorder, and it analyzes their vocal patterns and then matches it to their medical history, and they've actually developed a predictive function such that monitoring of these people's vocal patterns can predict whether they're going to go into a manic or depressive episode, and then sends an alert to their families or their doctors being like, hey, maybe you should be a bit careful with this person over the next few weeks. We also have seen that video games are actually really, really useful in medical treatments, particularly for treatment of mood disorders. So this is my area. Mood disorders are really prevalent in America. At least 20% of the population will be diagnosed with a mood disorder during their lifetime, and they're also really expensive. The economy loses about $80 billion a year due to mood disorders in both lost productivity and medical costs. Treatment for these illnesses is difficult. Antidepressants have a really high kind of tolerance or rejection rate, and the most effective treatment is generally therapy, but that's expensive, it's time consuming, it's difficult for people to get to the therapist twice a week, so on and so forth. This is where video games come in. Video games are actually a really effective and easily deliverable therapy to people who have mood disorders, where they can sit down and do it on their own time and do it as much as they need to. And this study used a therapeutic video game with older people who had depression. And what they found was that severity of depression decreased over 2 months of testing, and also the ability of these subjects to pay attention was improved on the Tovar task, which, as you remember from earlier, is that reaction task with the flashing visual stimuli over the 2 months of testing. So not only did they have an improvement in their depressive symptoms, they also had an improvement in cognitive function with video game therapy. And another example of video game therapy is used in treatment of post-traumatic stress disorder. Now, PTSD develops when you get a generalized stress response to a particular stimulus. And again, therapy is expensive and time-consuming. The most effective therapy is exposure therapy, where you expose someone to the stimulus over and over and over until it loses the stress response. And that is a difficult thing to set up, particularly for returned veterans who have really quite high levels of PTSD compared to the normal population. It's difficult to create a situation in which they encounter those stimuli regularly and on enough times to kind of dull the danger alert that goes off in their brain. And so again, this is where video games come in. You can create a stimulated environment where they encounter all of the things that set off their stress responses, and you run them through it often enough that they no longer get a stress response to these stimuli. So, as you see, many parts of the brain and associated skill sets are involved in programming, and you can improve these skill sets. Learning to program is like learning a new language and then learning to solve problems in that language. We could potentially improve programming itself to better fit with how our brains work. We have a lot of wetware in our head dedicated to doing particular things that we're not really taking advantage of at the moment, like facial processing. And you also see that there's a really big future in biomedical research for computer-aided therapies, and hopefully some of you might think about dedicating your skill set to that. I would like a programmable immune system. I think that would be cool. So thank you for attending, and thank you to John for having me back again this year. I can be found under this handle on all of these various channels. This was me last year. And this has now emerged into the world, and this is what you get when you cross a programmer with a neuroscientist. He's fairly cute. He's wandering around the conference. You can come say hi if you want to. And this is a bit of a tout for our job. So we're currently looking for a research fellow. We do pay academic wages. I know programmers are used to being paid more than your average bear. But it's a really cool project. We have really good conditions. We have excellent health insurance. We have 4 weeks of leave a year, 5 if you count the one you get for free over Christmas week as well. And it's interesting work. So we have a really big gene expression database of humans who have had, or human brains, from individuals who have a variety of mood disorders such as depression, bipolar, and schizophrenia, and also control brains. And we need someone who is good with statistics and programming to come in and help us deal with this database, because we've gotten to a point where the neuroscientists are throwing their hands up in the air and going, oh my God, this is really hard. So this is the link for that job if you would like to apply. If you want to come ask me more about it, then you're quite welcome to. Thank you.